Good day, everyone. Welcome to our Calculus 2 session for today. Today, we will tackle two major topics in integral calculus. We have indeterminate forms and improper integrals. These topics challenge us to go beyond simple limits and definite integral. We will explore how to evaluate expressions and integrals that seem unsolvable at first glance using power tool like the L'Hopital's rule and substitution techniques. We will divide today's discussion into four key parts, which is the first topic is all about the indeterminate form 0 over 0 and Cauchy's mean value theorem. This problem is a classic example of the 0 over 0 indeterminate form, and we will use L'Hopital's rule to find the limit. And for our letter B, we have the other indeterminate forms. Here, we encounter the indeterminate form infinity minus infinity, which requires us to approximate the behavior of function near zero. And for our third topic, we have the improper integrals with infinite limits of integration. This improper integral has an infinite upper limit, so we will approach it by changing variables and evaluating a limit of a definite integral. And for our fourth and last topic, we have other improper integrals. This problem involves a singularity at the endpoints where the function becomes undefined. We will solve it by recognizing a standard inverse trig integral. So with that overview in mind, let's begin with the first problem, exploring the indeterminate form 0 over 0 and applying powerful techniques to resolve it. Okay. So for our first problem, we have here limit as x approaches to 0, x minus tangent x over x multiplied to 1 minus cosine x. We need to start by identifying that both numerator and denominator tend to 0 as x approaches to 0, confirming it's a 0 over 0 or indeterminate form. So how do we do that? We will do it by applying the limit by substituting 0 to our x. So we will get 0 minus tangent 0 over 0 minus 1 cosine 0. And when we do the calculation here, tangent 0 is 0. Tangent 0 is 0. So we have 0 minus 0 over 0 minus cosine 0 is equals to 1. Cosine 0 is 1. Therefore, 1 minus 1, we also got 0. And since the limit is indeterminate, this is a great candidate for L'Hopital's rule, which we apply when a limit results in 0 over 0 or infinity over infinity. Since we got this indeterminate form, let's proceed to applying the L'Hopital's rule. Apply the L'Hopital's rule. This one here. Since the limit is indeterminate, we apply the L'Hopital's rule. Okay, let's proceed in applying the L'Hopital's rule. let's copy first our problem. Limit is x approaches to 0, x tangent x over x minus cosine x. Okay. To apply the L'Hopital's rule, we need to differentiate our numerator and our denominator. Okay, let's do it. So x approaches to 0. Okay, now let us derive first our numerator. This is where this part here will be the starting point where we need to be careful with how we derive certain functions. Okay, let's start. Well, the derivative of x is 1. Therefore, we write 1 minus the derivative of tangent x is secant x squared. Secant x squared. And since we were done in deriving our numerator, let us proceed to our denominator. Here we have case where we can what rule we can use in this case? In this case, we can use the product rule. Is it product rule? Yes, it is product rule. And the product rule states that d dx f of x g of x is equals to f of x, derivative of f of x multiplied by g of x plus the f of x and the derivative of our g of x. So now let us apply this product rule in our function here, which is our denominator. So for our x, or our f of x, we have our x, and our g of x is 1 minus cosine x. And to solve this, what is the derivative of our f of x, which is our x? The derivative of x is 1. So let's write 1 here. And copy our g of x, which is our 1 minus cosine. 1 minus cosine x plus, what is our f of x? We have x. And the derivative of our g of x, which is the 1 minus cosine x, the derivative of this is sine x. Because if we solve this thoroughly, we have 1 minus cosine x. Okay. The derivative of 1 is 0 minus the derivative of cosine x is negative sine x. Then we got this, and we distribute the sign, we will got 1 plus sine x, which simplify to sine x. Therefore, the derivative of this function is sine x. This sine x here. Okay. Can you still follow? Okay, let's proceed. And now that we got the derivative of our numerator and denominator, we can proceed to applying our limit. Let me just erase this here. Okay. Let us apply our limit. Secant 0 squared over, we can simplify this as 1 minus cosine 0 plus 0. Okay, we have sine 0 there. To solve this, we can use our scientific calculator for us to get the accurate answer. 1 minus secant 0 squared is equals to 1. You can check your scientific calculator for confirmation. Then 1 minus cosine 0 is equals to 1. Just like here, what we did here. 1 plus 0. Sine 0 is 0. There. Therefore, again, we have an indeterminate form. And since the limit is indeterminate form again, we still need to apply the L'Hopital's rule again. Okay. Since the limit is indeterminate, use the L'Hopital's rule. Okay. Now that the limit is indeterminate form, we will use again the L'Hopital's rule, which the same process we did in our previous solving. We need to get the derivative of our numerator and denominator. So our new function will be limit as x approaches to 0, 1 minus secant x squared over 1 minus cosine x plus x sine x. There. Now from here, we derive again our numerator and then our denominator. Okay, so how do we do that? Okay, let's start from our first term. We have 1, the derivative of 1 is 0. And the derivative of our secant x squared. Here, we will use the chain rule in deriving secant x squared. Secant x squared dx. Okay, let's start. Here, we can use chain rule. Okay. For our f of x, this is how I use chain rule for a simplified way of solving, to avoid confusion, or if you are confused with the chain rule form, you can use this simplified way of solving of mine. Our f of x is secant x squared, and here I will identify which one is x. Our x here will be secant x. Since we identify the f of x and x, we will derive the both, and we will multiply the both after we derive them. So the derivative of f of x is, here we can use the power rule. The power rule states that dx xn is equal to nx n minus 1. That is our power rule, and we will use this here in our f of x. So after that, with that being said, we will have 2 secant x. Since 2 minus 1 will equals to 1, then we don't need to put 1 as our exponent, since it is an imaginary number. Then our x, the derivative of our x, we will have the derivative of secant x is secant x tangent x. Then after that, we combine the both. We multiply the both. Then we will get 2 secant x tangent x here. But we can still simplify this as 2 secant x squared tangent x. Okay, so this is the derivative of secant x squared. So let's put this here in our original solving. We have 2 secant x squared tangent x over. Now that we got, let's not forget, we don't forget our sign. Since the derivative of 1 is 0 and the sign is still there, therefore we write the sign there also. Okay, for our denominator, this is a long process indeed. Okay, for our denominator, let us think about what derivative differentiation rule we can use. Okay, by analyzing the denominator, we can conclude that here in 1 minus cosine x, we can use like what we did earlier, like in 1 here. Let us do it again. So our 1 minus cosine, since we already solved this one earlier, we will write down the result like what we have earlier, which is sine x. Then we copy the operation. And now we got x sine x. What are we going to use in this case? We can use product rule again, since this is our first term and this is our second term. Okay, what is the rule in product rule again? Here we will derive our f of x. Our f of x is, let's write it down for clarification, d of x is equals to the derivative of f of x multiplied by g of x, g of x lang, plus our f of x multiply the derivative of our g of x. Okay, so now let us solve for our x sine x. The derivative of our f of x is, which is x, is 1. So let's put 1 here, and as is, copy our g of x, which is sine x, plus we have copy our f of x, which is x, then the derivative of our g of x, which is sine x, is cosine x. The derivative of our that involves trigonometry. Okay, now that we got the derivative of our numerator and denominator, let us again apply our limit. But before we apply our limit, let us simplify first the terms that we can still simplify. Let's delete this. Sorry guys, there should be a limit here. Limit as x approaches to 0. Now let us simplify our denominator, because we can still express it in a simplified form. 0 negative 2 secant x squared tangent x over sine x plus sine x, we will have 2 sine x. 2 sine x plus x cosine x. There. This is our simplified. This is the simplified form. And after this, let's apply our limit to get our answer. Okay, we have 2 secant 0 squared plus, no, there's no operation, tangent 0. 2 sine 0 plus 0 cosine 0. And from here, since we already applied the limit, we can use our cycle to calculate each value. We have negative 2 secant 0 squared is equals to 1. Then our tangent 0 is 0 over 2, copy the 2, sine 0 is 0 plus cosine 0 is 0. Then let us further simplify our answer. Negative 2 multiplied by 1, we had negative 2, then multiplied by 0, we still got 0 over 2 multiplied by 0 plus 0 is still 0. And since the limit is indeterminate, or we have the indeterminate form, let us again apply the L'Hopital's rule. Let's conclude this here. Since the limit is indeterminate, apply the L'Hopital's rule. Since the limit is indeterminate, apply the L'Hopital's rule. Again, like what we did earlier, we need to derive again the numerator and the denominator. For our new limit, therefore, for our new limit, which is our third time deriving, we will have limit as x approaches to 0, negative 2 secant x squared. I'm sorry for that. Secant x squared tangent x over 2 sine x plus x cosine x. And this is our new limit that we need to derive. So let's copy our limit as x approaches to 0. From here, let us use what is applicable, the differentiation rules, what is applicable in this case. For our numerator, let us use product rule. To derive our numerator, we can use product rule in this case. So let us copy our 2. Our first term will be secant. Our f of x will be secant x squared, and our g of x, we will have tangent x. Okay, let's try. Okay, first our f of x will be secant x squared. Secant x squared. So secant x squared. After this, the derivative of our g of x, which is our tangent x, the derivative of tangent x is secant squared x. Secant x squared. Secant x squared. Plus, you can use the product rule, then plus the derivative of our f of x, which we already have earlier when we use the chain rule. Let us copy the derivative of our secant x squared. We have 2 secant x squared tangent x, and our g of x, which is our tangent x. Now we have the derivative of our numerator. Can you still follow? Let us review it again. For our numerator, we derive the secant x squared tangent x. So first, we copy our f of x. We use the product rule here in deriving the secant x squared tangent x. Of our f of x is secant x, and our g of x is tangent x. First, in the rule of product rule, f of x multiplied by the derivative of our g of x, and our g of x is tangent x. Therefore, the derivative of tangent x is secant x squared plus our derivative of our f of x, which is secant squared x, and we already solved for it earlier. Therefore, the derivative of our secant x squared is 2 secant x squared tangent x, and we copy our g of x, which is tangent x. Therefore, this is our derivative. This is the derivative of our numerator. Can you still follow the solving? Okay. For our denominator, we can use, we already used the product rule, still product rule, like just like what we did in here, x sine x. The only difference is that here we have cosine x and earlier we have sine x. Let's do it like what we did earlier. Let's solve this like how we solve it kanina. So let's copy our 2 the derivative of our sine x is cosine x plus, let's use product rule again. We have 1, then the derivative of our, I copy the g of x. We will have cosine x plus copy our f of x, then the derivative of our g of x, which is the cosine x. The derivative of cosine x is negative sine x. There. We got now both the derivative of our numerator and the denominator. Now let's continue solving it. Let us simplify first the limit, the function, to avoid further confusion. We have secant x squared multiplied by secant x squared. We will have secant x fourth raised to 4 plus copy 2 secant x squared tangent x squared over cosine. We have cosine here and cosine here, so we can add this term here and this, so we will have 3 cosine x plus, we distribute the sign of our sign and the sign here, then we will got negative x sine x. And now that we simplify our numerator and denominator, we can now apply our limit. Wait, we can still simplify our numerator pa pala. Sorry. So we will have limit as x approaches to 0. Let us distribute our negative 2, which is, it's on the outside of the parenthesis. We'll have negative 2 multiplied by secant x raised to 4. We will have secant x raised to 4. Negative multiplied by positive, we will get negative 2, 4. 2 times 2, we'll have 4 secant x squared tangent x squared. That is our simplified answer for our numerator. And now that we are in this simplified form, we can now apply our limit. We have negative 2 secant 0 raised to 4 minus 4 secant 0 raised to 2 tangent 0 squared over 3 cosine 0 minus 0 sine 0. Okay. Let us use our cycle calculator, or you can use your mental computation on this one. Secant 0 raised to 4 is 1. 2. 1 minus 4. Secant 0 squared is also 1. Then tangent 0 squared is 0 over 3 cosine 0 is 1. Then sine 0 is 0. Now, negative 2 multiplied by 1, we have negative 2 minus 4 multiplied by 1 multiplied by 0, we will have 0 over 3 multiplied by 1, 3 minus 0. Therefore, we get the value of negative 2 thirds. And that is our answer. Finally, gotten this value, the negative 2 over 3 for our item number 1. Conclusion here will be, therefore, the limit exists, which is equal to negative 2 over 3. Okay. That will be for our problem number 1. So let's do a quick recap. First, we apply our limit for us to know whether the limit exists or not. And upon applying the limit, we got the indeterminate form, which is 0 over 0, and therefore we can apply the L'Hopital's rule. And upon applying the L'Hopital's rule, we need to derive our numerator and denominator, which also, after deriving the numerator and denominator, we apply the limit. And after applying the limit, we got our first indeterminate form, second indeterminate form again. Therefore, we use the L'Hopital's rule again and derive our numerator and denominator. We got these values here, and after we got these values, we apply again our limit, and upon applying the limit, we got indeterminate form again. And we can stop here. Therefore, we apply again the L'Hopital's rule. We got our third indeterminate form, and again we need to derive again and again until we get our value, our answer. And after the second deriving the numerator and the denominator, we have here these steps where we apply again the L'Hopital's rule. And apply the L'Hopital's rule again, derive numerator and denominator. We got these values here, and after simplifying, we apply our limit, and after those long steps, we got our limit, which is negative 2 over 3. Therefore, the limit exists. This is for our item number 1, which is all about the indeterminate form and the Cauchy mean value theorem. So the answer for this problem here is negative 2 thirds. Okay, let us proceed to our second item, which deals with the other indeterminate forms. Excuse me. Okay. Now, still, we need to do the first step, which first and foremost, we need to apply our limit to identify okay, first and foremost, first step that we need to do is to identify whether the limit exists. And by doing it, we need to apply our limit as y approaches to 0. I'll have I think it will be a tricky point if we let's proceed. 1 over ln 1 0. Okay, we have ln 1 plus 0 minus sine 0. Okay, now 1 over ln 1 0 minus 1 minus 0. This we can have infinity minus infinity. But since it is kind of tricky to use, we can simplify, or we can rewrite our given into something that is more easier to solve. We can do it like this. This is just for our first try. We got this indeterminate form, and let's try to solve this in a different way of solving by, let's say, rewrite our given. Let's get the LCD. No, the term is not LCD, but let's perform the operation. Then we have ln. Let's copy the denominator, the both term, sine y. Then from here we got sine y minus ln 1 plus y. This is the new version after we rewrite our original one. And this here, we can now apply our limit again for different approach. Okay, from here we will have sine 0 minus ln 1 plus 0 over ln 1 plus 0 sine 0. We use our scientific calculator for more accurate answer. Then we will get sine 0 is 0 plus minus ln 1 is 0 over ln 1 is 0 divided by 0, we get 0 over 0. And from here we express it as in the indeterminate form and this indeterminate form here. And since the limit is in indeterminate form, we should now can apply the L'Hopital's rule. Let us conclude it first. Since the limit is indeterminate, apply the L'Hopital's rule. That is L'Hopital's, not L'Hopital's. L'Hopital's rule. And from here, like we did earlier, let us derive our numerator and our denominator. Now let us copy our limit. Limit is x, no, not x, it is y. It's y. Y approaches to 0. What is a given? New given. We have sine y minus ln y plus ln 1 plus y over ln 1 multiplied by 1 plus y sine y. And from here, let us derive our numerator. Let's find the derivative of our numerator. What is the derivative of sine y? The derivative of sine y is cosine y. Cosine y, let's copy our sign. The derivative of ln multiplied by 1 plus y is 1 over y, no, not y, 1 over 1 plus y. It is in their identity that ln x is equals to 1 over x. Therefore, in this case, our x is 1 plus y. Therefore, the derivative of ln 1 multiplied by 1 plus y is 1 over 1 plus y. Then, let's do it in the same manner, like how we derive our numerator and our denominator. The derivative of our denominator will be the derivative of ln multiplied by 1 plus y is the same as like what we did. In our numerator, we have the derivative of our sine y is cosine y. No, got this all wrong. This is the power of you should analyze your problem thoroughly to avoid wrong answer. Here we should not derive it directly as term by term because we can use the product rule here. What do you think? Yes. This should not be like this. Now, let's use again our product rule. Our f of x is this one here, multiplied by our g of x. Product rule states that copy our f of x which is our ln 1 plus y, then the derivative of our g of x which is our sine y. The derivative of our sine y is cosine y. Cosine y plus the derivative of our f of x which is ln 1 plus y is 1 over 1 plus y. The derivative g of x, not the derivative because we already derived our f of x, so copy our g of x which is sine y. Let's not forget the thorough analysis of our problem to avoid mistakes. Okay. From here, since we were finished in deriving the numerator and denominator, we can now apply our limit. Cosine 0 minus 1 plus 0 over ln 1 plus 0 cosine 0 plus 1 over 1 plus 0 sine 0. Let us thoroughly check if we can get indeterminate form. Cosine 0 is 1. 1 minus 1 divided by 1 get 1. ln 1 plus 0 is 1. ln 1 is 0. Cosine 0 is 1 plus 1 divided by 1 we have 1. Sine 0 is 0. Therefore, we still got 0 over 0. Okay, let's conclude again. We get our second indeterminate form. Since the limit is indeterminate, apply the L'Hopital's rule. Okay. Now, we need to derive again our numerator and our denominator. So, our new given will be limit as y approaches to 0 cosine y minus 1 over 1 plus y over ln 1 plus y cosine y plus 1 plus y sine y. There. That will be our new numerator and denominator that we need to derive. Okay, let's copy our limit. Approaches to 0. Now, let us get the derivative of our cosine y. The derivative of cosine y is negative sine y. Sine y, copy our sine, and from here, Let us derive this here. Let's derive this term here. Have. Let's use other color. Have 1 over 1 plus y. You can write this as 1 plus y negative 1, and we use the power rule, then we will get negative 1 plus y negative 2. And from here, you can write this down as negative 1. Can you see it clearly? Sorry for the 1 there. Our power rule states that x n dx is equals to nxn minus 1. Do not forget our rule. We have, write this as 1 plus y squared. Rule of exponent. When we're going to put this down, this will be going to be a positive number, and if we were gonna be rewriting it, or we need to transform a fraction, the exponent of the denominator, if you're going to put it in as a whole equation, then you change the sign of the exponent. That is the rule of the exponent, exponential rule. Therefore, we have this answer here. Now that we have our derivative of our second term, let us plug it in our original solving. Okay. We have, that was negative, right? We got the negative sign, and since it is positive here, it is negative 1 over 1 plus y squared. This will be going to be positive. Be positive. It's going to be positive. Positive 1 over 1 plus y squared over. Now, let us derive our denominator. Are you familiar with the form? What should we use? What rule should we use? That's right. We can use again the product rule. That is right. You can use the product rule here for easier derivation. Now, let's label first the terms. We have f of x, and this one will be our g of x. Now let us proceed in deriving our denominator. Now, f of x, let us copy our f of x. We will have, first let's solve for this one first, and after this one. F of x, which is ln 1 plus y. The derivative of our g of x is negative sine x. We can put the sign here to avoid, for easier. We have sine L sine y multiplied by, no, plus, sorry for the multiplication, plus product rule plus the derivative of our f of x. What is the derivative of our f of x again? Yes, the 1 over x, which is 1 over 1 plus y. Copy our g of x. We have cosine y. Cosine y. There. Are we still in the same boat? Both? We are still deriving this one here. These terms. We are still not in here. Okay. Are we still on the same page, class? Okay, now let's proceed. Let's copy the sign here. We have plus. Let's do the same thing like what we did in our first case. Copy our f of x. We have 1 plus y what is the derivative of our g of x, which is our sine y? We have cosine y. Cosine y. Then, let's proceed here. Then, what is the derivative? No, what is the derivative of our f of x? Let's just put the formula. F of x g of x plus derivative of f of x then g of x. Cosine x, then let us have plus the derivative of our f of x. We did it here in our numerator, and the sign is positive. Now let's not just put the sign first to avoid confusion. We'll have negative 1 over 1 plus y squared. The derivative of our, copy our g of x, which is sine y. Sine y. There. We got its derivative. Let us simplify the denominator first. Now let me just delete these things. Okay, let me just push it, write it here in the corner for more space. So let's simplify our numerator and denominator. We have sine, this is the simplified form for our numerator, since we already distributed our sign earlier. Just here, we have negative here, then our original sign is negative here, and we got the derivative of this one is negative, and we distribute its sign to our original sign, which is negative, and then we got a positive sign. Now let's copy the original equation. Plus y 2 over, let's simplify our denominator. We have ln 1 plus y sine y plus, we have cosine plus cosine, we have 2 cosine y, this one here, these term. The result, when we perform the operation, we will get 2 cosine y over 1 plus y. There, minus, and this one here, we got distribute our sign, we'll have negative sign here, Then copy our sign. And we got sine y over 1 plus y squared. And that is our simplified form for our numerator and denominator. Now that we simplify, the last step will be applying our limit. Let's do it by substituting 0 to y to our function. Negative sine 0 plus 1 over 1 plus 0 squared. Then negative ln 1 plus 0 sine 0 plus 2 cosine 0 over 1 plus 0 minus sine 0 1 plus 0 2. Still with me? Now let us use again the purpose of our scientific calculator to avoid mistakes. Negative sine 0 is 0 plus 1 divide by 1 will have 1 over ln 1, negative ln 1 is 0. Sine 0 is 0 plus 2 cosine 0 is 2, 1 over 1 minus sine 0 is 0 over 1 times 1 is 1. Then let us simplify further when 0 plus 1, 1 over 0, 0 plus 2 multiplied by 1, 2 divide by 1, 2 minus 0, 2. Therefore, our final answer is 1/2. There you go. This is our final answer for item number 2. Conclusion, therefore, the limit exists, which is equals to 1/2. Okay, there you go. For our item number 2, we got its answer, which is 1/2. Okay, let us move on to our third item, which is improper integrals with infinite limits of integration. Here, the case here is that we need to apply certain definition for a certain problem. Like here, we have infinity, we have a upper bound, which is infinity, and our lower bound, which is 0. And the correct definition that we can use here is definition number 1, which is definition of improper integral with upper limit. If f is continuous for all x greater than or equal to a, then the integral of upper limit positive infinity with lower limit a f of x dx is equals to limit as b parang Julio to limit as b approaches to infinity ba dx 2 plus 2x plus 1 4. Let me rewrite the function. Write the definition, I mean. Definition 1. A f of x dx is equals to limit as b approaches to infinity ba f of x dx. And that's what we're gonna use in solving this problem. Okay, let us start. So, first thing we need to do is to integrate first our definite integral. I mean indefinite integral. Let us integrate first our indefinite integral. Okay, let's do it. Now we have here our indefinite integral is dx over 2x plus 1 raised to 4. For us to solve this, we can use u substitution. Okay, u substitution, where we let u is our 2x. We let 2x plus 1 is our u, and our du is 2 dx. And our dx is equals to du over 2. Let's put a boundary there. Okay, let us solve this further. Then you can write the expression as 2 plus 1 raised to 4 dx. Then substitute the u. You will have 1 over u raised to 4. Our dx is du over 2. Okay, now we have this. We can put our constant outside our integral. We will have u 4 raised to negative 4 du. The exponential rule, which is if you wanna put our denominator or rewrite our denominator is not a fraction form, then you can use our exponential form where our exponent will become negative. Just this one here, negative 4. Okay, now that we have that, let us perform integration. Half. Power rule again. No, this is not derivative. No, it's power rule. The power rule. It is the reverse of power rule for antiderivative, which states that xn dx is equals to xn n plus 1 over n plus 1 plus c. This is the power rule in antiderivative, which is the integration. We apply this in this problem here. Our x is u and our n is negative 4. Negative 4 minus plus 1 is negative 3 over our n is negative 4 plus 1, get negative 3. Negative 3 plus c. Okay, let's continue. Negative 3 1/2. Then let us multiply perform operation, we have 1 over 6, negative 6, the negative 6u raised to 3 plus c. Let us perform the exponential rule. 1, 6u 3 plus c. Then let's substitute back our value of our u, which is 2x plus 1. We have 6 2x plus 1 raised to 3 raised to 3 plus c. And that is the derivative. No, that will be the answer to our indefinite integral. This one here. Definite integral. Okay, let's plug this in our original solving. We have limit as b approaches to infinity. Our b is infinity and our a is equal to 0. 1 negative 1 over 6 1 over 6 2x plus 1 raised to 3. And now from here, let us apply its bounds. We have negative 1 6 2x plus 1 raised to 3 b 0. B to 0. Now we can okay. Let's continue. And from here, upper minus lower. Let us perform the upper minus lower limit. Bound. B approaches to infinity. We have negative 1 over. Our upper is equals to b, so 2b plus 1 3 minus lower bound is 0 minus 6 2 0 plus 1 3. There. If we substitute this, we simplify rather, we will have limit as b approaches to infinity. Negative 1, let's copy first our first 2 plus 1 3. Let's distribute the sign. Negative times negative, we have positive. We'll get positive 6 2 multiplied by 0 0 plus 1 1, then 1 raised to 3, we have 1 6 times 6, we have 6, so let's put 6 here. Okay, then after this, no, this is still b, since we still don't apply the limit. haven't applied the limit. So here we have still b. From here, applying the limit, negative 1 over 6 to infinity plus 1 raised to 3 plus 1, 6. We have infinity plus 1, 6, 1, 6. And therefore, this is our answer. Therefore, we conclude, since the limit exists, therefore, it is convergent. And that is the answer for our item number 3, which talks about improper integrals with infinite limits of integration. Now let's put the answer here. We have 1, 6 convergent. Now for our last item, we have the other improper integrals. Let us start answering this now. Okay, for our final item, the first step that we are going to do is to identify what definition should we use that is applicable to our problem. For this problem here, the definition that is applicable to this is our definition 5, which states that an improper integral with an infinite discontinuity at its upper limit, which means that if f is continuous at all x in the half open intend on the left a and b, and if limit is x approaches to a, f of x is equals to positive infinity, then integral that has the upper limit b and lower limit a f of x dx is equals to limit as t approaches to b to the left integral upper limit t lower limit a f of x dx if the limit exists. This means that our critical number will be b, which is our upper limit. Let's try to solve this for a more clear visual on how you can solve this kind of problem. Definition 6. Definition 5, I mean definition 5. BA over f of x dx is equals to limit as t approaches to b negative b to the left t ta f of x integral with upper limit t lower limit a dx. Let me rewrite it again in a proper way. Definition 5. Integral of BA out of f of x dx is equals to limit as t approaches to b to the left ta to the left ta f of x dx. Now let us try to use this definition in our problem here. So our critical number here is our upper limit, which is a. as t approaches to, our b is a, which is a, to the right, to the left, and our t is t, and our a is negative a. The a here is stands for its value. No, I mean the a here is our a. Our negative a here is the value for our a here. Copy our given dx over square root of a squared minus x squared. There. Now that we established our starting point, let's start to solve this by integrating our given limit. Let's first rewrite it for easier way of solving. We have t negative a 1 over dx. And now here comes the tricky part. This expression here is an inverse trigonometric function, and this expression here is equal to arc sine negative 1, no, I mean arc sine x over a. That is our inverse trigonometric function. This is negative 1. Arc sine x over a. From here, let's perform the lower and upper bound. Limit is t approaches to a to the left. We have arc sine x a t a. The rule upper minus lower, let's perform it. Upper minus lower, t approaches to a to the left. Upper minus lower, arc sine negative 1 ta minus arc sine, still arc sine, this is arc sine. We have negative a over a. Okay, now arc sine dA, arc sine, this is a constant, so we can divide it. A term that is divided to by itself will be equal to 1, and since we have negative in our numerator, then we will have negative 1. And now that we already have the value for we already solve or simplify our second term, let us now apply our limit. Therefore, we will have arc sine t a. Our t will be a, since we already apply our limit. Minus sine, let's put a bracket here. Arc sine negative 1 is negative pi over 2. Pi over 2. And from there, arc sine 1 plus, distribute the sine, we have pi over 2. And here, arc sine 1 is equals to pi over 2 plus pi over 2. Therefore, pi over 2 plus pi over 2, we have pi. Therefore, this is our final answer. Therefore, the limit exists. Therefore, since the limit exists, therefore it is convergent. Okay, now we got the value or the answer for our last problem, which is equals to negative, no, not negative, just equal to pi, convergent. To summarize our discussion or our lesson for today, our solving in the whole thing that we did, we saw how L'Hopital's rule handle tricky limits. We tackled also improper integrals by substitution and inverse trigonometric identities. These techniques expand our problem-solving toolbox beyond basic rules. So, thank you for learning with me today. Keep practicing these strategies. They will help us with advanced math, physics, and even real-world modeling. So that would be all for today's session. I hope you learned something and you can pause and you can watch again the video for clarification, or you can solve it by your own and you can compare your answer with the answer that we come up in this solving session. Until the next video, I hope this is not the last video. Bye.